this talk. I will talk about how to accelerate the XGBoost applications with GPU and Spark. There are two topics. One is for GPU and one for Spark. Just check the demo whether it can work well, because in the morning I showed another talk. I give the demo. I found the resolution is not good, but I think here maybe better. Okay. Another introduce for myself and my team member. Staff software engineer at DataWorks, and currently serving at the Spark PMC member and committer, and also contribute to other machine learning libraries like TensorFlow and Apache Spark. So I'm most working on the intersection with the system and the algorithm. And Mingjie is who did also a lot of work for this project, and some of the work still under working. He's software engineer at DataWorks and focus on Spark Circle and machine learning. He's a PhD from Purdue University. Okay, let's give some agenda of the talk. First is what is XGBoost, and why we want to integrate it with Spark, and why we need to running XGBoost on GPU. And after because this part of work has been finished by other persons, and what we are doing currently is running Spark, running XGBoost on Spark on GPU. So this is maybe after the demo we will talk about it. So due to the time limitation here, I will not go into the algorithm details and the formula derivations. So if you want to learn the details of the XGBoost, you can refer the paper. Okay. We should first let you know what is XGBoost. It's a gradient boost tree algorithms and the system developed by Tianqi Chen at University of Washington when he was a PhD. And after it been released, so it's widely used across industry from different companies. And very exciting features is it have win more than half of the winning solutions in the Kaggle competitions that using XGBoost, or some ensemble models that depends on the XGBoost. And it has supplied different kinds of APIs, such as Python, R, Java, Scala, and C++. It can run in CPU and GPU. And in the future, it can run on distributed and GPU. Currently, it can run in single node on Hadoop or on Spark and on Flink. So it should be suitable for most of your case if you have requirements for classification of regression. Okay, give a brief introduction of XGBoost. First, it's a tree-based model, which means it's a decision tree or something like that model. And second, it's a boosting tree model. And the third is a gradient boosting tree model. So what is a decision tree model? You can see the picture in this slide. It's usually used for classification or regression. For example, here we want to predict a person like computer games or not. So in the first level, we separate the samples based on the age of the person. If the age is no more than 15, we will go to the next levels. And the lower level, which means the next levels, we can separate it based on the gender of the person. Then we use the score on the leaf node to answer the predictive questions. A younger boy likes computer games more. So this is the split process of the Spark of the XGBoost, or maybe a distributed tree, maybe a decision tree models. So after you build one trace, we will use boosting. What is boosting? Boosting means we will build multi-models sequentially, which means one by one. And each new model is attempting to correct the errors of the previous models. So the score of the boosting models will be the sum of the scores in each tree. So it should be additive models. So the idea here is we will use multi-weaker learners to achieve a better performance than anyone alone. So this is the boosting. It means it will train multiple models, but it will train sequentially. So maybe someone will have confused why the models is trained, why the tree models or the single models is trained sequentially. We can make it parallel. This should be resolved when you finish the talk. Okay, and the gradient boosting is an extension of the boosting, where the process of generating weaker models is formulated as a gradient descent algorithms. Just like we use gradient descent to solve logistic regression. So usually the gradient descent will operate on an objective function, and XGBoost has its own objective function. You can refer the paper. So next is why the XGBoost is so silent. Because we advise that XGBoost is so powerful, then why it's so excellent? I think three perspectives is the main driven that XGBoost is so excellent. First, it uses second-order gradient over the loss function. You can refer all of the other gradient boost models before XGBoost. It only uses the first-order gradients in the loss function. What is the benefit of the second-order gradient loss function? You can imagine when we solve some convex optimization problems such as logistic regression, you can use different optimization methods such as SGD or BFGS or LBFGS. And the difference is SGD is the first-order optimization and LBFGS is the second-order optimization methods. The second-order optimization methods can help us to find the minimum value or find the solution very, very fast. So this is the benefit of the second gradient of the loss function for the XGBoost. And another benefit is in the XGBoost objective function, it contains some regularization terms. I think everyone has some machine learning background would know the regularization terms used. They will use for prevent overfit. So this will get the XGBoost to can prevent it from overfitting. And another great feature for the XGBoost is parallel tree construction. And this is most relevant to our talks today because we want to accelerate it. So we need to run multi-thread, run in batch, and run in distributed way. If the algorithms didn't support parallel from the mathematical perspective, we can't make it parallel. So the big benefit of XGBoost is from the algorithm itself, it can support parallel tree construction. We will show it later. Okay. And after we have known that XGBoost, we will want to know why we want to make the parallel. Despite some good performance relative to existing gradient boost tree implementations, XGBoost usually can be some time consuming to run because if your data is going large, you can take several hours to compute. So a very intuitive idea is to use parallel to accelerate it. So this is one of the motivation. And another motivation is if you use XGBoost, you will find there are a lot of parameters you need to tune the models. Because I think most of the users will not care about the internal implementation of XGBoost and the mathematical principle. They want to know how to set correct our parameters, and in your own problems, you can get a more accurate model. So usually you will do model tuning or hyperparameter tuning. You do some cross-validation. You set different parameters, and then you train different models. You get the best models. So this is another workload that it will take a lot of time. So this is the motivation of our work. For the model training, we can use GPU to accelerate. We can also use some distributed XGBoost to accelerate the training process. And for model evaluation, for model tuning, we need some frameworks. So Spark should be one of the best candidate for this kinds of workload. Okay, so this is the motivation of our work. In the following talk, we will talk how to accelerate the training and prediction first. And first, running XGBoost on GPU, and then running XGBoost in a distributed way. Because XGBoost has already supported running distributed, not tied with Spark. And then we will integrate the XGBoost with Spark. We will see some benefit, and then integrate it with the Spark ML pipeline to do some cross-validation or hyperparameter tuning. And I asked, if we want to run XGBoost on Spark on GPU, it will has a lot of dependency to deploy the work and install a lot of libraries before you run your workload. So Hadoop Yarn provide a good solution for us. We can use the Docker to run our job. So first, a very short introduction about XGBoost on GPU. Let's recall what we talked in last slides. We say that the XGBoost is parallel tree construction, which means you can build the XGBoost trees parallel. So let's say this picture. For example, when we split the node A, we'll get yes or no. We will get two nodes. In the CPU version of XGBoost, we can do it separately, which means we can use two threads to train to get split in the left node and the right node. So we can say this is the multi-thread implementation. But for the GPU version, we can also benefit from the multi-thread computation paradigms. And what else we can also do? This is currently the GPU version and the key features of the GPU version. Because in the CUDA, we have a very fast parallel prefix sum algorithms. What does it mean? It means in the original multi-thread paradigm, we will find the best split for the left node using one thread, and using another thread to find the best split for the right node. But each time, we will only process one simples. So in the GPU version, we can use them to process multiple simples. And it has algorithms. If we sort the node buckets in an order, we will get a fast parallel prefix sum algorithms and to fast split the node. So this is what the GPU accelerates the XGBoost. You can see some benchmarks, but from my experience, I have run the XGBoost on GPU for different workflows. It may be vary. The performance is not very, very consistent because I think it should be take a very careful configuration for your parameters. But generally, you can say this dataset is a binary classification problem with 11 million rows and about 30 features. So if you train such kinds of XGBoost model on a CPU, on a single node on multi-thread CPUs, it may be time-consuming work. So we can say we can train it on a NVIDIA P100 GPUs, and compared with the CPU has 32 cores. And we can say the blue line is the GPU version, and the orange line is the CPU version. We can say the GPU version will decrease, the text area of the GPU version will decrease more fast compared with the CPU version. So this is only single node accelerate. Okay, after that we will think if the data is getting bigger and bigger, the single node can't handle it, and even we don't can't put all the data in a single node memory, what we can do? We can try it to run the distributed XGBoost. But another issue will occur. We need to face another issue. Where the data come from? Usually, if we want to train XGBoost our classification model, the data is need to come from different source, and the data may have some missing value, may have duplicated data. We need to do some pre-processing for the data. And after the pre-processing, we get a clean data. Maybe we want to load the data in a distributed fashion and training it. So what this kinds of work is very, very suitable for Spark. So a very straightforward idea is we can use Spark to do the pre-processing, and then we can feed the data to distributed XGBoost. And actually, Nan Zhu from McGill University, he has a prototype for this. We can run it. Let's say, what's the challenge of the current implementation? Because we found we need to make Spark executors can communicate with XGBoost workers, because both of them are distributed. For example, we have 10 partitions, and meanwhile, we need to start like 10 XGBoost workers and train the XGBoost model in a distributed way. So we need to make Spark XGBoost can be taught at the execution layer and also at the memory layer. For example, we need to copy the data from the Spark partition to the XGBoost memory space. And another one is we can have the XGBoost algorithms in the Spark machine learning pipeline, but we also need to make it as other algorithms in Spark machine learning pipeline, such as we need to support the model persistence. The model can be evaluation, can be do cross-validation to find the best hyperparameters. So this is the most of the two challenges we should face. Let's see how we resolve it. So the first, let's say this is the distributed XGBoost architecture. It has a tracker and has in our example, has 4 workers. So in the distributed XGBoost, the 4 workers will talk with tracker, the tracker to coordinate the 4 workers to work. And you can say, at each worker, it will take a partition of training data sets. It means one part of the training data sets to compute some statistics locally. And then we use our reduce algorithms, like the MapReduce. And it will synchronize the states and finally get the total statistics to grow the tree. So, and for the synchronized of the workers, we use in SGBoost, we use Rabbit libraries. So this is different, totally non-relevant to Spark. It's a distributed SGBoost workflow. OK, let's see how we can plug it into the Spark architecture. So the first thing is we should start the SGBoost tracker in the Spark driver side, because both of them are actually as a master in the distributed running time. And as a Spark executor side, in each Spark executor, we will start a SGBoost worker. And then these workers will communicate with each other by the original outRadius layer. It means the SGBoost workers will talk with each other, but they don't talk other Spark executors, which is not co-located in the same machine. It means these SGBoost workers will talk with other SGBoost workers and talk with the Spark executors on the same machine, but didn't talk to other Spark executors. This is the execution paradigm of the Spark SGBoost integration. So there are some issues. The first issue is where is the data come from for the SGBoost worker? It will come from the Spark executor. It will come from some Spark RDD or data frame partition. So in the current implementation, we will first copy the data from Spark data frame space to the SGBoost memory space. This has some cost, but the cost is acceptable. We have did some performance test. We found it can be improved. And how we can improve this? The first idea is we can use like Apache Arrow, because currently Spark has supported to store the data in the Apache Arrow format, and the users can access the Apache Arrow. And the Apache Arrow has a lot of libraries which support zero copy between the Apache Arrow and the libraries like pandas or others. So one idea is we get the Spark data frame partition data stored in Apache Arrow, and then at SGBoost worker, we can directly compute it on the Arrow. Because the Arrow format is very standard, we don't need to worry about it will change later. OK. And another one is we can plug in the Spark SGBoost on Spark. Another one is how to implement SGBoost as an algorithm in Spark ML pipeline. So we can implement 3 wrappers for the algorithms. The first one is the SGBoost estimator. It inherits from the estimator in Spark ML Lab. It used to train the SGBoost model. And the SGBoost model, which is a transformer, which is used to make prediction based on the data frame data. And we have a lot of SGBoost parameters, like other parameters in the Spark ML pipeline. After we have this, we can do all the features like other algorithms in Spark ML Lab, such as we can do hyperparameter tunings with cross-validation. We can evaluate our model according binary classification logic or according regression metrics. And then we can also support the pipeline and the model persistent. We will show the demo later. OK, this is the performance for SGBoost Spark, and compare with the native Spark GBT classifier. Because I have been complained by a lot of friends who use the Spark GBT classifier, and they also said it has not so good performance. So you can say the SGBoost on Spark is almost 10 times faster than the MLlab GBT cluster. So, but there are still some improvement space. OK, let's show the demo. I wish the demo can work well. I think everyone can hear it, can see it. OK. The demo is we will use a famous data set, IRS. I think it's almost like the hello world in machine learning area. We have downloaded the dataset from a website and store as a CVS. So the first step is we will load the dataset. We can say there are 5 columns for the dataset, and this is the data. Totally 150 dataset. And then after we load the dataset, you can say we will do training and text split. You can say we will get a training dataset which has 115 samples. After that, we will check whether the training data is the label is balanced, because if the label is imbalance, we can't get good models. So we'll do some statistic based on the data set. You can say we can also try to select other view of the dataset, because if you have a lot of classifiers, maybe the table data is not so intuitive to get the result. Okay, and after that, we will construct our machine learning pipeline. And the machine learning pipeline has 4 steps. The first is, because we have 4 columns as a feature, we need to assemble them together into a Spark vector. Otherwise, we can't put it into the model feeding. So first is we assemble the feature into a single vector column. And the second step is we will index the string labels, because the machine learning models can't recognize labels other than 0, 1, the double data. So, but currently our label is string, so we need to convert the strings to double values. And the third step is we will add XGBoost classification estimator to make the classification model. And then the last step, we need to convert back the model, because in the model training, we convert the labels into double values. So we need to convert back to the string values. So this is the pipeline. Let's start to run it. And we can also specify some parameters for the XGBoost estimator. For example, the number of iterations, which means we'll generate 20 trays. And the number of workers is the number of distributed workers of XGBoost, and which is the objective function, and the number of class, and some other parameters. And after we get the model, we can do a prediction on the text data. You can say, this is the species, this is the original label. And we assemble the 4 columns together to get the vector of the features. And this is the index label, which is 0, 1, 2. And this is a prediction result, which is also a double value. And the last is the predicted labels. We convert back the double label to the string label. So this is very fast training. So usually, we want to know it's a good model or not. We use some evaluator to get some metrics of the model. For example, we can try to get the accuracy of the model. You can say the accuracy is about 93%. So it should be a good model. Okay, it should be a good model, but this is because our data is so small data. Usually, in your case, you will need to do a lot of parameter tuning, hyperparameter tuning, to find the best parameters, which means the best model. So let's show how to do the hyperparameter tuning. Let's say it's almost like other MLab algorithms, and say we can specify a parameter grid. We can set the XGBoost max steps for 3 and 8. And another parameters is eta. We can say that is 0.2 and 0.6. So we have 4 parameter combinations. Now we want to find which one is the best combinations. So it will take some time to running. You can say there are 4 parameter candidates, and we will train 4 models at least. And we currently set the cross-validation number for these 3. So it means we will split the training data into 3 parts. And first train on the first 2 parts to use the left part for testing, and then the third and the second and third part for training, the first part for testing. So we will also, it will means we will train 12 models. So it will take some time for the cross-validation. This is because my cluster has only several nodes and has a lot of other workload. So in your case, maybe you have more strong clusters, and this may take less time. And for the cross-validation, the new Spark 2.3, it has been supported to submit the Spark jobs parallel, which means the 12 jobs that we mentioned, we can submit them together if you have enough resource. So, but in this case, I didn't show the features. It maybe if we set the parallelism 3 or 4, we can get more speed, a quick training for this. Oh, it's still not finished. Okay, almost finished, I think. Oh, after we have got the best model, what we should do? We should still do some model evaluation. We want to get the best parameters. Oh, we have got it. No, still not. The progress is not accurate because several jobs. Yeah, we have get it finished. And after that, we can say, because we only want to choose the best models for the XGBoost, so we only concern about the XGBoost stage. So we can get the best model of the best boost model. You can see the training summary of the XGBoost model. At last, the error loss is 0. It means almost overfit. So this is because our training data set is so small. And you can see the eta 0.6 is the best eta. So we can get the best parameters. And because the space is limited, we didn't print all the parameters. So we have a lot of parameters for the XGBoost to set. So this is why the experienced machine learning engineer can get a better model to use XGBoost. But the junior machine learning engineers don't have get the best models. Okay, we have built the pipeline, and now using cross-validation, we can get good models. After that, let's show we want to save the model. Because the models we have get good models, maybe other teams want to use it, so we need to save it. Let's show it has been saved at on HDFS. Yeah, because in the Spark ML lab, the pipeline models, we will have 2 directories. The first one is the metadata, and the second one is the stage of the pipeline models. Okay. After we have saved the models, maybe other teams or other colleges want to use this model. This one who didn't train the model. So let's suppose we are new users. We can load the model from the HDFS and do some prediction based on the new data set. So you can say, based on the model, we get prediction result. You can say this is the original label columns, and this is the prediction label columns. Maybe some of the prediction is correct, and maybe others maybe not correct. So this is the whole process for the Spark XGBoost integrations. And you can say you don't need to involve anything about XGBoost, which means the interface are very, very familiar with the MLab pipeline. What you should do is just, let's say, the configuration of this job. You only need to add the Spark JAS. The JAS contains the XGBoost Spark integrations. When you submit your Spark job, you just submit the JAS together. So this is the only modification for your job. And another very experienced practice is we need to set the exact calls and the exact instance. Let's recall how Spark deep learning, how Spark XGBoost work together. At each partitions, it will start a new XGBoost worker. So if in each executors, if you don't have enough calls, enough CPU resource, you can't start the worker. So I say in the XGBoost Spark integration GitHub, I found a lot of users complaints that their jobs were hung. But when I checked the configuration of the job, I found this said default number of calls for each executor, which is 1. So it should not work well. So we need to care about these parameters when you submit your Spark job. Okay. Let's finish the job. When we finish the demo, let's talk about the feature works. Two of the work is undergoing. The first is we will use Apache Arrow to reduce the memory copy between the Spark and the native XGBoost memory space. Our another solution, candidate solution, is ND4J, which is used for deep learning 4J. It can directly access some memory, native memory space, and don't need to copy it. We would more prefer to use the Apache Arrow solutions. And another one is, can we run distributed XGBoost on GPU? Because we just talk XGBoost can run in GPU, but we don't show it can run on distributed XGBoost on GPU. So this is another issue we should consider about. We have some tests for this and maybe release some work later. So another issue is we want to talk about accelerate the XGBoost with Spark and GPU. Accelerate not only means accelerate the training process or the model cross-validation hyperparameter tuning process. It also relevant to the developing and deploying. If we want to try use some GPU resource, we need to some framework to help us to management GPUs and to do some isolation of the GPUs. And another issue is for the GPU driver, we need to configuration. For the XGBoost dependency, we also need to carefully configure it before we start work. So another issue is we can run this job in Spark on Docker, in Spark in Docker on YARN. So maybe the same issues like running Spark deep learning pipeline on YARN. So if you're interested in these topics, you can refer some of my talks this morning, and we can also I will also show some examples and demos at this URL. So I didn't upload the tutorials. After the summit, I will upload it. Oh, this is the reference of the work. OK, I think that's my talk. Thank you. Do you have any questions? OK. Oh, reference. OK. You can download the slides after the summit. Yeah. Any other questions? No? OK. OK, I think this is a very, very good question. It will involve us for some discussion about we should use a very strong single node machine with equipped with good GPUs, good CPUs. And another way is we can use some distributed solutions, such as Spark. But in the Spark cluster, in each node, maybe the power of your machine is not so strong. So, so I think we can't give a general solution or general advice for this because it depends on which kinds of your workload you run. For example, we can imagine that what's the difference from deep learning and big data? You can say in the big data area, we use some tools like Spark or Hive to processing data. The data is very, very large, and the I/O is usually the bound. But CPU may not need a lot of CPU and memories. And for deep learning job, you can say the input maybe not so much. For the ImageNet, you can say ImageNet, the raw data, the training data may be I think maybe I forgot it, maybe several gigabytes or tens of several tens gigabytes. So it's not very, very big compared with big data. For example, in the big data, a lot of Hive-based data warehouse has several petabytes data set. So if you're training a deep learning model, maybe the single node with very strong GPUs, CPUs should be a good solution or a better solution in the current situation because in the current there is no very, very good distributed deep learning frameworks. So it's easy to set up a single node environment for your deep learning pipelines. But for XGBoost, I think XGBoost with more, we should be good at show some structured data machine learning, which means like the image data or video data or signal data is maybe not so good to solve such kind of problems. So we use GPU to accelerate the XGBoost. It can get less benefit compared with deep learning. So this is why we not only to focus on build a very strong single node for the XGBoost. I think this is some of my view of this, maybe not so correct. OK, no problem. Any other question? OK. OK. Yeah. 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 Yeah, I think this is some of the Spark cross-validation issues. Just like I say, in the new Spark 2.3, we can support the submit multi-jobs. So if your cross-validation will running 100 jobs, in the old implementation, it will submit one by one, which means the first job finished and then you submit the second. But in the new Spark 2.3 implementation, we support submit different jobs together, which means if your cluster has enough resource, you can submit the 100 job at one time and training. You don't need to wait for any jobs to finish. So this should be, I think this is for the cross-validation case, not for the XGBoost. Other algorithms will benefit from this. Yeah, but long-running jobs maybe you need to write your own jobs, but you can't use the framework. Okay. Any other questions? If no, okay, thank you.